All right, good afternoon, everyone. My name is Michael Dickens. I'm a research scientist with Texas A&M High Performance Research Computing, and I will be covering the first part of this short course. And the second part will be a hands-on tutorial presented by Gaya Yadav. I just want to make sure everyone can hear me and they can see my screen. So can we get a thumbs up? Make sure everyone can see the first slide. Okay, good. All right. So this is an outline of what I'll cover in the first part of the course. Everyone, hopefully you've got your academic license ID. You can get one from CryoSPARC. It's free for academic users. When you do have that license, you can only launch one CryoSPARC job on that license, basically one per user. So you can't start a CryoSPARC job on one computer and then go to another one and launch another job, because it actually connects to the CryoSPARC server and recognizes that you have a session open. So on our systems, you can only launch one CryoSPARC job at a time. We'll go over some resources limitations, and we'll start CryoSPARC on the ACES portal and go over a few other things, and then we'll have the interactive tutorial session. This is where you can download the license. It's I'll show you the format in a little bit. You'll need that to launch the CryoSPARC job. So we have a CryoSPARC interactive app on ACES, and we have an open on-demand portal where you can access the user interface. This is an image of our ACES computer. We've got a number of GPUs and some other specialized nodes that these other specialized nodes are not supported by CryoSPARC, but we'll be able to use the H100s or the A30 GPUs. We have 30 H100s and 6 A30s. This is a composable cluster, so at times we may have only 2 H100s connected per node. Other times we may have 8 H100s connected per node, and that can change. And I'll show you how to see the current status configuration. When you do start a CryoSPARC job, make sure you specify enough wall time to process your files. Make sure it would be good to overschedule. If you plan on working one day, go ahead and schedule for 2 or 3 days, and then when you're finished working, you can cancel the job, so it'll free up resources. It's easier to cancel the job than to request the job extension on a Friday afternoon, hoping that the staff sees it before your job ends. And if you launch a job and resources are busy and it doesn't start right away, and you need to leave, you want to go ahead and cancel that job, because it may launch while you're away and it'll be using up resources while you're sleeping overnight if you leave it open. All right, so you can only launch one CryoSPARC session at a time, but within that CryoSPARC session, you can run multiple jobs. CryoSPARC has its own scheduler where you can select the number of GPUs that you started the job with. So if you start a job with 4 GPUs and you're running in your CryoSPARC session, you run 4 different jobs, each using 1 GPU. You can do it that way. But if you're just running one job, then you may only need to use 1 GPU. So you can launch your job with just 1 GPU. Some tasks do not require GPU. CryoSPARC will let you know if it requires GPU for that task. And GPUs can get busy at times, and again, cancel your job if you're going to be away for a long time. You don't want to leave a pending job and go to sleep and then come in the next morning and it's been sitting idle for 8 hours or however long you sleep. Submitting jobs, there can be a delay start time due to unavailability, or we may have a scheduled maintenance, and we'll show you how to check whether there is a maintenance scheduled. Okay, so what we want to do is access the portal. So we're going to go to our main webpage, hprc.tamu.edu. and select the portal tab and then select ACES portal. So from here, go to portal, ACES portal. Now, if you haven't logged into Access yet, you'll see this page first where you need to select your Exceed ID, the identity provider, and then use your Access ID and Access password. So we'll give everyone just a minute to log into ACES. And then you'll also, there's a Duo two-factor authentication you'll have step after this. So I've already logged in. So once you're logged in, you'll see this page. So show me hands up if you, once you've reached this page, so we can see how many people we have logged into ACES. And if you have any questions during the course, just please unmute yourself and ask, or you can ask your question in the chat. You can see on the message of the day for ACES, there was a maintenance on October 10th. That has been completed. Okay, does anyone need any help getting connected to ACES? You do have to already have had your Access ID. And to launch CryoSPARC, you will have already had to have your academic license. Both of those can take a day or more. Okay, so what we're going to do is if you haven't launched CryoSPARC before, we're not going to use the CryoSPARC app. We're going to use the CryoSPARC short course app. Okay, if you don't have an Access ID, this course is being recorded. So once you get your Access ID, you can log back in and follow through the course. We will have the example file still available. Okay, so the CryoSPARC short course, we have some notes reserved so that we can assure that you can start a job. So this is what your license ID format will look like, and you don't want to use my license ID. You want to use your own, but I have to put it in this form. So if you haven't launched CryoSPARC before, there is a first step to initialize the database. So you can only select CPU. So launch with CPU first to initialize the database, and then go ahead and log in to the CryoSPARC interface, and then you can select accept the license, and then you can log out, cancel the job, and start a GPU job. So go ahead and start. There's only one version here. Paste your license ID there. You can, the minimum is 3 hours, but it'll only take a few minutes to do this part. So we're going to go ahead and start the CPU only job. So now it says it's sitting in queue. There's the username and password. Everyone's session has the same username and password, but the files are all saved to your Scratch directory, so no one can use your session. Okay, so it's starting. It's going to take a while, just a few minutes to start. And while that's starting, let's go to cluster shell access. We're going to access the terminal. And so cluster shell access. So here you can see message of the day for the terminal. You can see your quotas. And we want to run, let's do the maintenance first. So run the maintenance command, and this will let you know if we have a scheduled maintenance coming up. And right now you can see we don't have a scheduled maintenance. When we have a scheduled maintenance, the cluster will be offline usually for 1 day from 9 a.m. to about 6 p.m. Central Time. All right. So now we want to see, using the GPU avail command, we're able to see how the GPUs are configured. GPU eval. And we can see there's some PVC GPUs. We have 21 nodes that have 4 PVC GPUs attached. Now, CryoSPARC doesn't support the PVC GPUs, only the H100s and the A30s. So we've got 3 nodes that have 4 H100s attached. There's 2 nodes that have 8 H100s attached, and there's 1 node that has only 2 H100s attached. We actually have a reserve node. This is one of them right here. You can see there's 1 job already running on this node that has 1 of the GPUs. So there's 3 more GPUs available that can run on this node. And this configuration can change. You can see right now it's different than when I created this slide. Okay, we went over the maintenance, and if there is a maintenance, you'll see something like this. It'll show you the countdown. So if you wanted to try to squeeze a job in before maintenance, if you saw this time, then you could start a job with 3 days and 20 hours. And if it launches within an hour, then you can run a session there. But if you started a 7-day job when there's a maintenance scheduled in 3 days, then your job will remain pending, and it will only start after the maintenance is complete. All right, so let's go ahead and go back to our CryoSPARC session. Oh, what happened here? Let me see. I'm going to start another session. Did anyone have success getting their CryoSPARC session? Okay, everyone else got their CryoSPARC session started? I'm going to try that again. Okay, so once your session starts, you see this launch CryoSPARC button. You can click that button. If you want to, you can increase the image quality. It may not matter if you're just running jobs, but when you start to review the images, I think this will help. But it may slow down a little bit, just because it's sending more data over the network. So go ahead and click that and log in with these credentials. And then when you do, you'll see this commercial license agreement, and then go ahead and click accept. And then just wait about a minute, and then cancel your job. So let's see how many people were able to accept the license. Okay, we have 1 person that's logged into the CryoSPARC, and they accepted the license. Does anyone else have any issues, or were they able to accept the license? Just raise your hand if you were able to accept the license. I see 1 person. I'm going to try on my account. I'm going to try with the regular CryoSPARC job, since we have CPU nodes available. Okay, so once you log in and you accepted the license, then you can delete your CryoSPARC job and launch a new job. So where you delete your job is, you'll see it right here. You can delete your job here, delete your job, and then when you go to the CryoSPARC short course page again, you'll be able to select a GPU node, and you'll need a GPU node for the tutorial session. So go ahead and delete your CryoSPARC CPU only job and then launch a new, don't select CryoSPARC, select CryoSPARC short course. And then select, you can select 3 hours and then select the H100 GPU. And you can only select one GPU and then go ahead and launch that. And that'll be the session that we use for the interactive tutorial. All right, so let's see a show of hands. If you're able to launch the GPU job and access the CryoSPARC GUI. Okay, I'm just going to go back through the steps right quick. So from our main web page, you go to portal, you click access, portal, ACES portal access. And you'll see a page like this on the left side. Then you'll select your identity provider, click log on, and then you'll see this page where you put your access ID and your access password. If you haven't registered for access, there's a link here. And then you can follow along the course, the recorded course at a later date. Okay. So I want to go over each CryoSPARC session that you run. We'll create some usage stats, and you can access these in your session ID. It'll basically show you your the CPU usage and GPU usage for your session. So in this case, the percent load for CPU, you can see it's in red, so a very low CPU usage. The memory, the motherboard memory or RAM is less than 10 gigabytes here. I'm sorry, the gigabytes of memory is on the right in blue, so you can see it's about 10 gigabytes. And then you can see the GPU. You can see the percent load on the GPU in red and the amount of memory that was used of the GPU during various steps of processing. So that's automatically created each time. And the way you access that is you go to the CryoSPARC page again, go at the very bottom. Go to the very bottom of the launch page. And there's this data, right below the launch page, there's the data root directory. In the data root directory, select output and then sort on the modified time. Put the newest time at the top. And then you can click the session ID and you'll be able to click on these images and see the images. This is these actually get generated while you're running. So these images get updated every 2 minutes. So you can check if you want to see the usage stats while your job is running. All right, we do have group data directories. If you have a lot of data you want to share with your group, you'll need to send a request to create a group directory, and then you can input that group directory in the optional group directory to mount text field. And these are just examples of what you might enter there. Okay, so when the course is over, you can take a short course survey, and we have some more information about reaching out if you have any issues working on our cluster. So let's go ahead and see how many people we have connected to a CryoSPARC session with a GPU. If you can raise your hand, I see one. Jeffrey has his hand raised. Do we have one person connected? Do we have anyone else? I think we had one other person that didn't have an access ID. So if you have any questions, go ahead and unmute yourself and ask before we go to the next interactive tutorial session. You cannot share license ID. The license ID is for individual user. If someone takes my license ID, then I can't launch CryoSPARC because they've got a session open. So I have to put that field in there. In the future, I'm going to see if I can make this like a password field. But you have to use your own license ID. All right, so we'll go ahead and go to the second part of the course, and this will be presented by Gaya Yadav. He's the Cryo-EM Technical Director at the Laboratory for Biomolecular Structure and Dynamics here at Texas A&M.
Can you enable this screen sharing? Okay, so thank you, Mike, for the introduction. So as Mike said, my name is Gaya Yadav. I'm a technical director here at the Laboratory of Biomolecular Structure and Dynamics, Department of Biochemistry and Biophysics at Texas A&M. So today I'm going to give an overview, a brief overview of the facility here in the Department of Biochemistry and Biophysics, and then also tell you what different capabilities we have, and then we will quickly go to the data processing using the CryoSPARC for the single particle analysis. So first, the overview of the for LBSD. So here I'm showing the different equipments available at the LBSD. So that on the left is the glow discharge. So we use this to make the grades hydrophilic so that our sample adhere on the grades, because grades have a, not all, but most of the contact foil grades have a carbon film that is hydrophilic. So if we load the sample on that without making them so sorry, the carbon film that's hydrophobic, and if we don't make it hydrophilic, our sample will not adhere very well on the grades. So we glow discharge them to make them hydrophilic, and then use the Vitrobot as the semi-automated kind of robot to plunge the grades. It's not a robot, but it's just plunger. And then after we vitrify our samples and then use the pattern kiosk to image them. We have the latest the pattern kiosk of G4i, and our pattern kiosk is equipped with the different imaging the options. First, we have the best in the market. I would say best in market, the camera is called K3 direct electron detection. We also have a biocontinuum imaging filter and phase plate. We also have the regular CTD camera, basically used for the microelectron diffraction work. Here is the capability. Here is the limits, not limit, but say I can say the whatever the resolution, the highest resolution we got from our microscope. So this is you can see that's the workflow data. Once our system was installed, we did the workflow validation. So you can see it's from the apophytin. You can clearly see the holes in the aromatic ring. So the resolution is around 1.5 angstrom. Here is showing 1.7, but afterwards we improved, we did more processing, and we able to reach to the 1.56 angstrom. So here the different capabilities. We can do the single particle analysis. We can do the tomography. We don't have right now the film miller, but we are in the process of getting that. And we can do the microelectron diffraction and the data collection, and then the data processing for the difficult to crystallize the protein or the small molecule sample. Here's the typical workflow for the single particle analysis. So you have a sample, you freeze the grades, and then you do imaging. Then and then you collect the data, and then you obviously use the something like HPRC or some cluster system to process the data, and then you get the map, and then you do the model building, and finally kind of structure. You do the, if you have a inhibitor or some kind of drug molecule bound to the protein, you can do the how it's bound to the, how the small molecule or drug molecule bound protein or protein complex. Here is the some softwares used for the Cryo-EM data processing. So the best used these days are Reline and CryoSPARC. Reline is it's kind of slow as compared to the CryoSPARC, so people like to use the CryoSPARC the first hand. And then EMAN, iMode, and CPN. iMode is also is basically more used for the tomography data processing. EMAN is also back few years earlier. The EMAN is good, but not anymore. It's a lot of it's a slow and also a lot of hassles in installing and making it happen. So these days the CryoSPARC is the easy to use. So the most of the people are using CryoSPARC and Reliant for their data processing. So next, let's go to the real workflow. Okay, so that's the workflow. You have data, you do the motion correction, then CTF, then you, after CTF correction, you need to always, like when we collect the data, we have some bad data. So the micrograph curation, we remove that bad data, and then we do the particle picking, 2D classification, and 3D classification, heterogeneous refinement, homogeneous refinement, and then finally uniform, local, and post-processing. We can go back and forth for this, to iterate this process to improve the resolution. But that's kind of like the whole process for the single particle analysis, and then you get the final structure. Then you go and do the modeling and then refinement. Okay, so let's go to the real data processing. Otherwise, we will run out the time. Okay, so Mike already told you guys how to launch the CryoSPARC. I use the same procedure to launch the CryoSPARC. So here is the CryoSPARC. When you launch the CryoSPARC, you will see something like this kind of window. So it shows up like something like this. So what you need to do, first step is to create the project. So how to create the project? If you go here in the right top corner, you see the new project. You can click the new project, and then it will show up the new window. You can put the title. Let's say, okay, the tutorial October 2024, and then that's the title of the project. And then you need to define where is you want to save your data. So you need to click this folder. It will so open up this pop-up window. You can define the path for the directory where you want to save the data, process the data. So here we're going to save in the scratch. Okay, and then training. So you type the scratch. If you hit the enter, it will show up all the folders. training, and under the training, you should see the CryoSPARC here. Under the CryoSPARC, you see the Cryo-EM center. Then you have epoferritin. Go to epoferritin, and then you choose the demo. You can for the storing the process data, you can save wherever you want in your directory. Here, this is for me, so I can save it here. But you have to choose training after for me it's scratch training, but you have to choose your data storage where you want to save the files. So like you see that here a lot of folders, but I can save here. Okay, so Cryo-EM center, select, and then you can also create the workplace, workspace at the same time when you're creating the project. But you can also create them later on. So for now, I would say I will create a new workspace. So I say the October 22, 2024. Oh no, so I guess I can only store in my space, not in Scratch. Then you have to go your user YADAV. Yes, you have to go users. And then you see that I have users, different users, and u.ac. Sorry, I have to select find the username.
Can we use the search function on top?
Can you use the search box?
I don't, can we?
Start with first name or start with last name?
Yours will be u.gy.
This one. There is two GY.
Your GY122.
122. Okay, let's see here.
u.gy122.
U.
122.665.
Okay, sorry, thank you. So we can, you have to save the files. So you have to select the space that's specified for your user. So otherwise it will complain like, okay, you don't have right permissions. So now you see that gone. And now you can hit the create. Now you see that the next the screen will show up let's have a different options. So it's empty showing there because we don't have anything right now. So it's showing the empty space. So first step is to import the movies. So if you have a movie stacks, usually most of the data collected these days are the movie stacks. So you import the movie stacks. But if you have already like motion corrected movie, or you collected the micrograph not as a movie stacks, then you can choose, okay, import the micrographs. But since we have a movie stack, so we select, okay, we're going to import the movies. When you click the import the movies, it will show up this, open up this import movie tab. So what you need to do, you need to provide where are your movies. So do again the same thing, click the folder, and then now you have to go to the previous location where we saved our movie files. So if you go here, then you go training. So you go to Scratch, then training, then CryoSPARC, Cryo-EM Center, Epoferritin, demo, then you see the movie folders. I remove all other files, so here you only see the fractions.tif file. So you select one of them, one of these TIFF files, and then you have to use the wildcard to select all the files. So I remove everything, all the text except everything except the fractions.tif, because when you collect the data, you have different files. So you have a fractions.tif or fractions.mrc, and then you will have a JPEG images, and then also one text file that contains all the information about the data collection, or on what the dose and everything is used for the data collection. So you want to select the TIFF file that have a fractions, or some other identification, and then if you click this, it will also show up all the images. Then you say select, and then you also, when each mic, since we are using camera, each camera have this detector have some gain file. So each detector have a different gain file. So when you collect the data, wherever you collect the data, the facility need to provide the gain file. So if you go here, so you see I saved the gain file here. You can say select that one and then say yes. Okay. If if your detector is old, you might have some defects. So if there is some defects, the facility need to provide your defect file. You can also import that here. But our detector is new, so we don't have any problem right now. So we don't have any defect file. So another thing is flip gain reference and defect file on X. So most of the, not necessarily, but most of the detectors, when we collect the data, they have a different orientation as compared to when we save the files, the movie stacks. So you need to know what is the orientation of the camera and the saved file. Based on that, you need to flip and rotate the gain file. For our camera, for this data set, we only have a flip on Y. So we only say, okay, flip on Y, there is no rotation or something. So we just simply say, okay, just flip against Y. And then you need to provide some basic information. What is the raw pixel size? So here is the raw pixel size. You can see here. So the pixel size is, the data was collected at 300 kb. Pixel size is 0.326. So we put 0.326 here, and the microscope runs at 300 kV. So most of the new microscope have 2.7, that's called aberration, spherical aberration correct, CS correction. And we use 42 electrons for the total dose over the 40 frames in 1.5 or 2 seconds of total exposure. So you need to know these parameters to process the data. Okay, and that's roughly you need all. If the data was collected in EAR mode, then you also need to provide how many fractions are here. But this data was not collected using the EAR mode, so that's all the parameters you need for to import the movies. Once you fill up all this information, you say, okay, run queue the job, and then it will run the launch the job. If everything works, everything is detected, everything is important, it will finish. Otherwise, it will show up error. Based on the error it show up, you need to modify and then re-import it. So here you can see we already imported 25 movies. So we want to make it fast. So we only want to process 25 images. You can here you can see some of the first few images it show up, and then not all of them. So you can see the apophyton particles. They look fuzzy right now. So because they are movie images, what this when it software import is simply combine all the we call integrate all the movie frames and show up the integrated image here. So it's not motion corrected. So there might be a little bit drift in between the frames, so the image is not that crispy. So next step is to run the motion correction to make these micrographs more the particle looks more crispy. So either you can, there's two ways you can schedule the next job. Either you can go to the job builder and say, okay, patch motion, or this is the new version of the CryoSPARC. You can simply go here and say, okay, you look for the next job. So you say that the build the patch motion, click that one, then it show up, it automatically get all the inputs, whatever is needed. And then you can change all these parameters. Usually the most important thing here, you want to change it. Only thing, if your data was collected in super resolution mode, that's what it's happened done for this data. So your data is, you can see here, the images are 8K by 11K. They are huge. So you want to reduce the size to make the processing faster. So you may need to crop the images. So crop by half, that's the Fourier cropping. So it will not lose the resolution information, but it's reduce the size of the image. You also want to put the override the total dose. So we know that we applied 42 electrons for the total dose. If there is some hot pixels, that need to be removed from the data. So the cutoff we put is, okay, whatever we applied, we put the 42. That's our limit. We cannot go beyond that. If anything beyond that, that means something is wrong. So we want to replace that pixel with whatever we applied here. Okay, and then you need to also give the information how many GPUs you can use, because here we only have one GPU, and I cannot change it. But if you can request 4, you can put here the 4 GPU, and then it will use the 4 GPU to make the processing fast. You once fill all the information, you say Q, will run it. So roughly it takes around 7 to 10 seconds per movie stack. So we only have 25. So 25 times, if we take 10 to 50 seconds, that's roughly a couple of 3 minutes, 4 minutes. And also that depends on the type of GPU. If you have a lower memory GPU, obviously it's going to take longer. But these GPUs are fast, so it might be faster. While it's doing the patch motion correction, we can schedule another job. So if you click on these 3 buttons, you see that these 3 dots, you can see the list of the next action. So build the patch CTF estimation. You can build the CTF find. So that's the different software, CTF find 4 that you can also use the local motion correction, but usually we use for initial processing, we use the patch CTF. That kind of fast. So when you start the job, queue the job from from here, it will automatically take all the input files from the previous job. So you can already see that on the right side, he already took the micrographs from the job 2. Excuse me. So usually you don't need to change any parameters. Defaults work very well. The only thing you need to change it again the number of GPU you have using. So you can queue the job while even though its previous job is not finished, still you can queue the job, and you can queue whole procedure while so it will not wait for your input, and it will start the next job. Okay, so while it's running, let's go over and see how many finish. So you can go here and see you want to look. You can go select where you want to check. So you can okay, I want to see the top of the starting, what happened, how is it started, and then you can also see okay, what's the latest going on right now. It automatically go here. Also have input parameters. All the parameters are saved here. So if you don't make a note and you forgot what I did, you can come over later and then you open the job and you can open this and see okay what I used, and use the same thing for the other data sets. In the output, you will have a different files here. So you can look it and then metadata, what is doing the processing. So I have the metadata. So usually we don't need these things. We just need we need to wait until it's finished. And while it's you can see it's already finished. Once
Gaya,
it finished, yep.
We have one question to go over the patch motion correction settings again.
Okay. So if you click here in the the job builder, the patch motion correction, then you can redo this. You can open this the import movie, and then you can even simply drag from here to there. You select you get the input file, whatever the import file from the import job, and then here is the number of movies plot. So usually we see the 10 to 15 movies, how it's the fitting looks, but we don't want to plot everything, because we're not going to sit here and watching each one. So as long as 10 to 15 images look good, we just simply leave it 10 or 15. Only you can also select, let's say you have a few hundred, like 100,000, few 100,000 images, and you want to process not all of them. You only want to process few hundred or 100. You can provide here, okay, I only want to process 100 images out of 5,000. So it will only process 100 and then stop, and then it will save all the results for you. But you cannot do like, okay, you have 5,000 images and then you finish 100 and then stop, kill the job, and you want to use the 100 processed one. CryoSPARC will not allow you to use that the processed images. So whatever the images, whatever the job you run, you need to make sure it's finished. Otherwise, the output will not be available for next job. So if you have more movies, you only want to process fraction, you just provide, okay, I want to process 200, 500,000, something, whatever number you want, and mix and wait until it's finished. Then motion correction alignments. So it's use the, it don't go to the very high resolution, use the 5 angstrom, filter images to 5 angstrom, and then based on the features on the different fractions, it measures the drift between the different frames, and then remove that drift and then align the images. That's what it's doing. So you can also provide, okay, some people do like, okay, so initial few fractions have a higher, like more, we have seen that have a higher drift as compared to the later on images. Some people like to exclude some starting frame. So let's say I have a 40 frame. I want to exclude 3 frames from a start, yeah, and few last frames, because we know that the dose is accumulated over the time on the sample. So it has been seen that the later fraction have more the resolution loss as compared to the initial fractions. So some people like to remove that as well. So we have, let's say we have a 40. I want to use only 35. I want to remove last 5 frames that have a more resolution loss. So that's you can also use that, but usually because with the current detectors, people process whole frames. Next is output crop. So the cropping means we reducing, binning the data by 2. That's what the crop means here. So that's the Fourier crop. It's not like crop the image and discard the rest of the image. It's just to shrink whole image to half. That's what is called Fourier crop. So we use half because our images, the data was collected in super resolution mode. These images are 8K by 11K, you can see here. And if you want to process this data, it will be really, really time taking. So to make the process faster and increase the noise to signal to noise ratio, you want to crop it. And then again, you want to put the override, the whatever the dose you use, the total dose. You don't want to, if there is any hot pixel on the image, obviously that's going to have the higher dose as compared to what we applied. So we want to replace that pixel from the image with the total dose we applied. So that's the override the dose. And then number of GPUs, how many GPUs you have available, you can select here and then queue the job. Is that clear or anything else? Okay, now once the patch CTF was finished, you have to look on these things. You see that these the different plots. So you want to look this as the amplitude, so plus minus, and then here is the fitting. So you can see here, so what the fit resolution is there. So you have the theoretical value and then experimental value. Where the two values cross each other, that's the resolution limit, that's the fit value. So here you see that we have black, that's the theoretical value for the CTF, that's contrast transfer function, and then red is our theoretical value. So it's the cutoff is somewhere in the green line. That's 2.17. Then sometimes they are not very accurate, but that's roughly the same, roughly correct. So we want to next step is to remove the images that have a bad CTF fitting. Bad CTF fitting means they have a higher resolution, a lower resolution cutoff. So 2, if they are like 6 or 7 cutoff, then that means that's a bad. So what the next job is, you can curate the job, the exposure curation. So it automatically takes all the information from this, from the patch CTF, and then it will wait for a user's input. So what you need to do it, you go here, and then you look for the CTF fit resolution. So you see that since these are 25 images, they are manually selected images. So we don't have any bad image that have like fitting 4 angstrom or 6 angstrom. They all are fitting 2.14 to 2.9. So we don't need to discard any. But if let's say if you have some images that have this value is 10, then you can change the value here, and then it will discard that image. But here we don't need to change anything, and whatever threshold you want to select, you put that value and set that threshold, and then it will show up, okay, how many images are accepted and how many rejected. But here, since we don't want to reject anything, so it's still all 0 rejected. And that's the one parameter you want to set. Then another parameter is, that's the most important one. You can also select the total full frame distance. That's motion distance. So from it's calculating like from one edge to other edge, how much the drift, how much is the motion. So some have very good one. You see that's 10. Some 1 or 2 have like 50 nanometer, 50 angstrom the drift, but it's okay. So 50 is not that high. And you can also there is a list of micrograph with the different parameters. So here you have astigmatism. You can list and sort them, and you can select, okay, I want to discard this. So you select this and then say deselect that one. You can also select based on the tilt angle, the defocus value, and basically we using this CTF fit and astigmatism. If astigmatism is more than 500 angstrom, we usually don't want to use it, hamper the resolution. So once you happy with all the parameters and selections, you say, okay, there is more options to select. You can go through one by one and then set the value for it, and then discard the bad images. Once you're happy with all these parameters, it's done, and then it will save the selected image. Since we did not discard anything, the everything is selected. But if let's say if we discard 10%, this circle will be like a high. So some are rejected, orange and the teal. So that you will see that. So the next step is to pick the particle. So what we do for picking, we do first you can do the block picker. If you have already have some template, you can also use the template to expedite the processing procedure. But we want to go through everything. So you can also, if you would want to do, you can also do the manual picking, but you have to do one by one and extract it. So we go first the block picker, and then in the block picker, if you start the job from this, it automatically take the input, but you have to provide the value for the particles. So there's the two important parameters you need to provide. That's the minimum and the maximum diameter of the particle. So based on the protein size, you can go to if you have PDB, you can open in a Chimera, measure the diameter, longest diameter for the particle, and you can use that one, longest and lowest diameter, and then you can use that value and put it here. We are using ferritin So we know roughly what is the value. So the longest we know around 130 to 140, and then it should be around 80, I guess. But yeah, so you can use 100. So 100 to 140. You can also define what kind of a blob you want. You want to use the circular blob, or you have elongated particles. You can say, okay, I want it elliptical. Or you want, if you have ring shaped some particles, you can use that. Different options. You can also provide the, okay, I want to filter my template. So here we don't have a template, so it's fine. And then how many number of micrographs you want to plot. So 10 is okay. 10 is roughly fine. And then the number of micrographs you want to process, the same as I mentioned in the motion correction. If you have so many, you can say, okay, I only want to process 100 and get the template from the block picker, and then use that template for the template picking for more accurate picking. So here we can use all of them. Don't 25 images, not going to take long. And then you say, okay, start. And if you go here, you can hit quick. So you can see the picking, not great, but it's okay. It's picking most of the particles. So what we can do it next is to remove the ice and the background pick. So what we can do it, we go and set up the inspect the particle pick. So the inspect particle, we go and change the parameters to make the more accurate picking. So you see that it's waiting for our input. You can also provide the values, and then it can automatically use that value to filter out the picking. So you can see that there is some of them, their background picked. We don't want that. So there's two parameters here that need to be changed that will improve the picking. So it's called the power of histogram. So to remove the particle picked in background, you need to increase the power. So you see that it's removed the particle picks from the background. So you can choose, slide it, and see which one is best. You can also try to change the different micrograph. Looks good for everyone or just for one. And then another thing we need to find, let's see whether I can find. So you see that there's some dark, though even though it's a cluster of like multiple particles set together. Right. But we have somewhere, let's say if we have some eyes, let's say this is eyes. So, and usually the eyes have the higher contrast here. So you need to reduce the power, histogram power, to unselect the particles picked in the eye from the eyes. So keep dragging down. See that? So you can remove, and now it's kind of looks good to me. Still, there is some that's not look good, but it's fine. We can remove during the 2D classification. That's the one thing, power of the histogram. Another thing is you need to NCC score. So that's also can remove the particles that's selected from the background. Okay, so that looks good to me. But you can change. You can use your own decision, make your own decision to judge whether the picking is good or not. Once you're happy with this picking, you can say, okay, done picking. And then it's fast. The next step is to extract these particles from the micrograph. So you can say build the extract from the micrograph, the CPU, build extract from the micrograph GPU. So since we have a GPU, I would say GPU, the number of GPU. So here, now you have to, when you extract, so during the extraction, what you need to do it, you need to pay attention for the box size, what the box size supposed to be for the extraction. So the rule of thumb for the box size extraction is the box size supposed to be at least 1.5 to 2 times higher than the longest particle size. So that's the formula you can use to define to calculate the box size. So we know the particle size and the epiphet in the diameter is around 140. So that means we need around 140 means around 250 to 300, 280, 250 to 280 angstrom, the box size. And if you remember here, during the import, we used the pixel size 0.326. But during the motion correction, we crop the images by half. That means the pixel size become double. That means 0.326 times 2, 0.326 times 2. So our pixel size is right now 652. And we want the box size at least 140 times 1.6. That's the minimum. So 224. Our pixel size is 0.652. So the box size will be divided by 0.652. So we need to have minimum the box size we need to extract is 340. So this is not a very good number. So we want to keep the number that can divisible, that can make the smallest rational number. So I will use the 384. That slightly higher than that required, but it's also a good number. You can also go to the CryoSPARC website and tutorial. They mention like what kind of grid box and the box size are good and for data processing. So you can check that one. So 384, and I want to make even more faster the data processing for initial processing. I would say I'm going to bin it again one more time. So I'm going to bin one more time. That's 192. So now the pixel size will become even double. So the pixel size 0.652 times 2. So 1.3. So our at this pixel size, our resolution limit is 2 times 2. That's 2.6. So we can reach, even at this pixel size, we should be able to reach around 3 angstrom without any problem. So, and then you put these values and then say Q. Obviously going to, let's see whether it's using. Yeah, it's started. Okay. Next step, you can see here that the particle pics, they looks quite good. And from here it's already done. So the next step is we run the 2D classification to remove to discard the junk particles. So you can directly go to build the 2D classification, and then you need to provide how many 2D class averages you need. So that depends on the number of particles you have. Here we have a total, around 8,000 particles. So usually we want to keep a minimum around 100 to 200 particles per class average. So for this small data set, I would say 50 is more than enough. And then the maximum resolution you want. So it's also when it's do the 2D classification of particles, it do the iteration, and then whatever the resolution you mentioned here, it will go to that. So for the 2D classification, we don't need to go too high. And then alignment resolution, I say, okay, just align it to 8 angstrom to make it faster. But you can leave it empty, so it will go whatever the value it can reach. So you can also provide the mask, but we don't need right now. If you're providing a mask is specifically useful if you have a small particle, because when you have a small particle, signal to noise ratio is not very great. So providing a mask help. But for this apophytin, we don't need. But if you want, you can provide. Since we know that particle size is around 140, we can provide 150 to 160 angstrom mask. That will make the 2D classes looks better. Okay, then if your particle picking is not very centered, you can say increase this value to improve the centering. Even you do that with the default, it still is okay, but I usually put it at 0.5 to make it force it to center them. And then to make the classification better separated, initial online iterations, usually 20 works well for this kind of particles, but if you have small particles or difficult data sets, you need to increase this to 30 or 40 iterations. So for this, it's okay, this 20 is enough. And if you want, you can increase, it's not going to take too long. Okay, and then since we have only one GPU, we're going to use one, but if you have 4, you can put the 4x4 GPU. That will make the process. And then you launch it. You can see here that the particles, so right now it's only using few particles for the classification. So it's over the iterations, it's keeping adding more and more particles. So you will see they look for as long as go higher and higher on the iterations, the particle will be looks and the classes will look better and better. So you can already start to see the circle, the sphere for the apophytin, and some of them you can even start to see some features inside the sphere. So it's only have 8,000 particles, so the process is really fast. If you have, depends on the number of particles, it's obviously going to take longer if you have millions of particles. You can already see that it's only the 8th iteration. You can already see the good 2D class averages. So while it's running, we can set up another job, next job. So the next job is Q 2D class averages. Selected 2D class averages, you can do the build the balance 2D classes. For initial 2D class average classification, we don't need to balance. We need to get the good class averages and remove the bad ones. So say the select good one. Okay, so once it's queued, waiting for the inputs are not ready. So you can select, you can queue all the jobs on the subsequent jobs from this. And if you don't want, if it does not need any user interference, it can run automatically one after the other. So once the 2D classification will finish, it will start the select 2D class average, but we need to manually select them, so it will wait for the user input. But if we don't need any user input, it will automatically start the next job, and it will go over to the next the following job. So if you already have the selected and pick the particles, you can schedule all the jobs and then it can go away, and then it will run all. So you can now see the good ones are populated, and then bad ones are on the bottom. So, and you will see once we select this and we go back and do the picking, you will see that right now here, they are not, the picking is not very well centered. But if you, once we select the template from that 2D classification job and use that as a template for the particle picking, you will see that we have a very good class average, very good picking. Okay, so the 2D classification finished, and then it's waiting for our input. So you see that we're going to select all the good ones. Since we're going to use these as a template, we don't need to select all. We can only select the one which looks centered, because these are the appropriate in the different orientations are more or less same. So not really matters like how many 2D class averages you need use for the template picking. So few 2 to 3 2D class averages are good enough for the template picking. So I'm going to use 1, 2, and this looks a little bit different. So okay, I just select the 4. Okay, and this we will use as a template. So we can go here again. Okay, and you can because we're going to use this the micrograph, so we can go here and say build another job, build the template picture. It automatically select the exposures, and what we need to do is highlight click on the template, pick templates we want to use for the picking, and see that the micrographs are there. We need the template. So you drag these templates to input. Say selected now. And then again, you need to provide the diameter of the particles. Here, you don't need to provide the range, you only provide the diameter. And if you go to the 2D classification, it should show the somehow it's not showing the scale, but oh, it's hey Mike, it's the older version of the CryoSPARC. So the newer version of CryoSPARC show the scale here. So you can roughly know what is the size of your particle here. So you can use for the template picker, if you don't know the size of the particle, exact size, you can use as a reference to put that value here. So to put the value, and I have the exposures and then templates, and then you can view it. And you will see here the particle pickings is way better than the blob picking. You can see that it's way more centered as compared to the previous one. Now we do the same thing. We can inspect. Okay, you can see the part picking is way more centered as compared to the previous one. But again, we need to remove some of the, might also pick up some from the background. So you can remove that one, and also from the black. area, and that's what I need. Okay, said yes, done. Okay, now we do the same thing again. Extract from the box. Micrograph, 1 GPU, 384, 384, 192. Launched, we can, after the once it's extracted, we can meanwhile set up the 2D classification. Even though we try to discard the particles during the inspection, we still might have the particle that's not good. So after the 2D classification, we will be able to discard the bad one. So again, we don't need the, this is only 30. And 1 GPU, job. So now you can see our classes are, the 2D class averages are more centered. Previous one have more, more of, if you compare this one with this one. Oh, this is the final one, so we cannot really compare them, but still you can see some are at the edge, some are on the center. But if you compare, but once it's finished, this one, you will see most of them are in center. And also, we not this time we did not even force the particles to go to the center. We forcing, but we're not forcing the centering factor is only 0.2, not 0.5. And you can see here the particles are more centered, and then more like not that many class averages as compared to the block. So it's already discarded a lot of. You selected 13,000. And another thing is you might notice it. With the template picker, we have more particle as compared to block picker. So we got 13,000. Previously, we only have around 8,000. So we'll see how many we get after this discarding this bad class averages. But initial picking is around 13,000. We got 1, 2, 3, 4, 5 class averages. That looks good.
Hey, Gaya, while this is running, let's take like a 10-minute break,
Okay.
and we'll come back at 3:15. It'll take a little bit for that to run, right?
Oh, it will not take long. It's already done.
Okay. Okay. Well, let's take a 10-minute break.
Or maybe we can run. We start another job that takes like 5 to 10 minutes.
Okay.
And we take the break.
Okay. Sounds good.
Okay. So the next step is again select the 2D class averages, and we'll need our users input. So we select these 4 good ones, 5, and then we want to discard. Even though they might have some good one here, this one, but may not be as good as other ones. So we will go and go with the good ones. Okay, so that's the 2D class averages. So the next job is we want to do if you have a reference map from the structure PDB or ACES or some other sources, AlphaFold model, you can use that one. Or if you don't have any information or AlphaFold model does not look great to you, you can use these particles to generate the 3D model from the data you have. So what do you need to do for that? Go to these 3 dots And you can see the build 2D classification, selected particle with 2D class excluded, and build ab initio reconstruction. So we want to do ab initio reconstruction by using these particles to build the 3D model. So what we don't want to change much in here, much lot of parameters. We want to run it is under the default parameters. Only thing I usually do it, I ask multiple ab initio classes. So the data might be some particles very good, some are not very good. So that can classify into 2 or 3 class averages, and the one which looks good we can use for further processing. So let's say we use we want 3, and then you can keep rest of the parameters default. If you have a lot of particles, you can also define how many particles you want. Let's say you have millions of particles. You don't want to use all of them. That takes so long. So you say, okay, only use 100,000 or 200,000 particles for the initial reconstruction. And then you can use that initial reconstruction for the 3D classification or heterogeneous refinement, and then make it a little faster as compared to the ab initio reconstruction. Because ab initio reconstruction only uses one GPU. It doesn't matter how many GPUs are available. It only uses one. So you put the value here, how many ab initio classes you want, and then you just simply say, okay, hit the queue the job. And this might take a few minutes, so you can take the break at this moment, this step. Okay, so let's start again. So you can see the job has already been finished, and if we ask for 3 class averages from the data, you can this in the new CryoSPARC, you can see that have different options. You can look into that, and then you can also even look on the how the volume looks like. The whether it looks better, which one look good, which one is bad. You can slide the threshold here, change the threshold, and you can see here how it looks. So that's the first volume. It's ab initio volume created by the job. So looks like it's not very. You're not going to get high resolution. It's only limited. Maximum you can get it around. It's restrict the resolution around 10, the 12 angstrom, right to 10 to 12 angstrom. But you can see some of the features. That's the number 0, class 0. Let's see the class number 1. And also more or less looks similar. It might be some slight variation between the two. But third one is look like it's not good. It's just simply the raw. We don't have any features. So what we can do it, we can we can remove the particle that belongs to this class, and the best practice is run the heterogeneous refinement after this. So you can run if you have so many particles, you can run you can run the heterogeneous refinement, homogeneous or homogeneous refinement directly for the class averages. But I like to do the heterogeneous refinement first and then better classify the particles. So to build the heterogeneous classification from the ab initio, it automatically takes all the inputs, particle stacks and volumes from the ab initio job. You can define the symmetry, what symmetry you want to apply. But at this stage, we don't want to apply any symmetry. So let's just keep it the C1. And then another thing is number of full iterations you want. Once it's classified into classes, classify the particle into 3 different classes, and then able to, like, there is no variation between the particle, no change in the number of particles between the class averages. There is always some shift between the class averages, but if it's not significant, then it will say, you see that if it is 5%, it's less than 5%, then it's called it, the data was converged, and then it will run through more iterations. That's a final iteration, and then it will end up. So you can say, okay, you can keep the settings this, or you can reduce this value to make it more stringent. But for now, we will keep it as the default. And this job is also take a couple of minutes for this many of particles. So after selecting, we will again have 8,000 particles. So we'll see how long it will take, a couple of minutes. And after that, we will see if the two class averages still looks similar, we can combine those two, or we can, there is an option, you can do the homogeneous refinement or non-uniform refinement, or another possibility, you can run the 3D classification after this, and then we can regroup the class averages based on the similarity, and then you can run the homogeneous. But I'm sure, like, if I run the 3D classification using these and use, and these two class averages, they're going to be combined together. But you can define how many class averages, how many class averages you need, you want to combine. Like, let's say you classify into 10, some of the class averages look similar, but others not. Then you can say, okay, classify into 3 groups. And then the class average that looks more similar, they will be classified into one group as compared to the other one. So we can run the 3D classification, or we can run the homogeneous refinement and non-uniform refinement after this is done. So you can see here, our pixel size is 1.6 something, 1.3, sorry. But it's also, it has its own way of, it's a bin. When it start the refinement, it bin by a bin to, I guess, the box size to 28. That means it's highly bin, so the resolution is always going to be very low. But over the time, you will see it improve quickly. Could not see much. See that here, almost nothing. You can see here, the most of the particles are classified into class 0. Out of 8,600, around 8,600, 6,800 are classified into class. And so let's see how we have. Sometimes heterogeneous refinement, if you don't have enough particles, it can mess the things up, but not all the time. So there is other ways of the data on the particle pickings, different softwares. This is the one we used. There is another. This version is older version. There is another option in this the newer version. You can after the motion correction and CTF fitting, you can run the, we call the denoiser. Yeah, here you don't have the option, but the new version have the called the micrograph denoiser. So like it's doing the same thing what we do uh, with the blurring and everything. So you can use that micrograph denoiser, and that will improve the contrast of the particles way better than what we can see here. So while it's running, we can go to some. Okay, it looks like it's taking too long. Maybe delete. Okay, so I'm going to kill this because we don't want to waste time here. So what we can do it, you can run the heterogeneous refinement and then do the same thing as here. We can select the good ones and do the what I'm going to do here, I'm going to select the good one. Let's say either of one of these two, and then I will run the non-uniform refinement. I'm going to run non-uniform refinement, and you will see. You can also run the homogeneous refinement and then non-uniform refinement, but can directly go to the non-uniform refinement and then with the C1 and then C2 the before the symmetry, and then apply the symmetry and see how the symmetry affects. So we can select the particles from here. We're not going to select all of them. We can select the particles that belong to class 0 and the class 1. And then we can use either class 0 or class 1 as the initial reference. And still we're going to use the C1 symmetry and say that it's completed. And then we don't need to use change a lot of parameters here. And one thing you need to change it whether you want to limit the alignment resolution. Other than that, you don't change any parameter. Like you want to change this, or you want to run more, let's say converged. After converged data was converged, you still want to run a few more iterations to make sure uh, converged very well. So you can run it, and you will see here the iteration coordinates refinement statement for the load. You can see here the threshold, it's a dynamic mask, 6 cents. And the load, the higher end, and then it's have lower end, the cutoff for the mask. And once it's started, it will take, it will be faster. You can start to see this, the central slices for the volume, the constructed volume. So that's iteration 0. And in the non-uniform refinement and homogeneous refinement, it also plot the FSC curve. So what the FSC curve is, Fourier cell correlation. What is the Fourier cell correlation? It's kind of same as it's based on the similar principle as in X-ray crystallography for the R factor. So it divide the data into two fractions, two halves, and do the reconstruction for first half and second half, and then overlap the two maps from the two half data sets, and then see how was the correlation between the two maps. So the correlation, the match between the two maps, the cutoff of the Fourier and correlation, and that will be the cutoff of. That's what the FSC curve here shows. So you can see the cutoff is the 10 angstrom, and then in Cryo-EM we using the number for FSC curve, using 0.143, and then where this curve cut that the value at 0.143, you see the line that's drawn at 0.143 value. So the place where it cut the FSC curve cut this line, that's the resolution limit of the map. Usually at the low resolution, they're not very accurate, but once it's especially for the small data set, it might not be that accurate, kind of accurate. But you can see that the resolution is improving very well at every step, every iteration. And also the resolution is also plot the linear plot that tells you how much noise you have. So the more noisier data, I mean the ice thickness, noisier means more thicker ice, will get higher B factor, and that will affect your resolution. So the lower, the thinner ice, better particle, better the B and lower B factor, that's improved the higher resolution. So we also look on this, we look on the resolution limit cutoff, and also look the B factor, how the B factor improve over the different iterations. You can see already start to see the helices density, helices, and improve the resolution, and it's improving the B factor. The previous iterations is 700 something, now it's already improved 350. And you will see once it goes to 6-7 iteration, it will go below the around 150. You see here, the B factor, you can see that only 45. So that one is the same data, but we used a lot more images, around 3,000 images to process the process. And then we get around 1.56 angstrom resolution. But here from 25 images, we targeting to get around 2.5, 2.6 angstrom resolution, not more than that. But once currently we are processing in C1 symmetry, so the resolution will be the lower as compared to when we apply that. You can see that 357 is close to 288, and then the map will make more sense now. You can see here, you can clearly see the density that looks like the helices. Okay, so once this finished, and also the pixel sizes are around pixel. We've been doing our data for 2 to 4 times. So pixel size is also the high right now. So the resolution will also be affected by the pixel size. We can go and re-extract the good particles, and then we do refinement to improve the resolution at lower pixel. Might run one, two, it's improving. 288 to 240 fast. Let's see how it goes. And then once it's finished, the next step is we're going to apply the symmetry. We can also do the 3D classification and local refinement, these things, and we can also do the sharpening, which also improve the resolution. Local refinement, global refinement, 3D variability. If you have a very heterogeneous data, and you can do the 3D variability analysis. That will tell you how variable is your data, and then based on that, you can classify into the main class. But here, we're not going through all those steps, but we're going to do the we're going to do the quick processing. So next step we do again. Actually, the next step is the CTF refinement, and then redo the non-uniform refinement. That will take longer and will not be able to finish in the time. You can already see that the B factor goes to what? This is not correct. The previous iteration, the B factor is around 81. So it's improved. So I'm setting up, while it's running, I'm setting up another job for the non-uniform refinement with higher symmetry. You can see already it's 3.87 angstrom. This somehow it messed up. It's not good, not the correct. So like we can use the parameter, the output from the job 18, the non-uniform refinement, and we can also restrict this radius, and we can apply the symmetry. So we know that it have a um, this have 24, so it's these 4. So let's see. Finished. We know that every have the octahedral symmetry, so we can just apply octahedral symmetry here. And why it's important? Because our data is so tiny here, there are only 8,000 particles. So that's why you see that here you cannot properly calculate the refractor. See that it's only showing 12, that's not correct. So when we apply the symmetry, that octahedral means our apparent amount of data is 8 times higher. So we have 8,000 times 8. So overall the data will be higher, and then that can improve these parameters. So when you use the octahedral symmetry and you rerun it, you see the effect. And it will also be the faster because only need to do alignment 1/8 of the. So you can already see the effect of the symmetry. When we did the previous non-uniform refinement, the first iteration was really cannot really see that much density. Distance. Here is already first iteration. You can see the density very well. It's way more intense as compared to the previous one, and you will see this FSC curve will improve very quickly. In time, let me open the VNC. So we can use the VNC and launch the Chimera X to build this to, to look on in camera, the map camera. You can see how good now the FSC curve, and it's improved the resolution immediately to 2.272. And then also the linear plot, the linear plot is way better, it's way more fitting is better than the previous one, and also the map quality. to look here, the map quality as compared to the previous one, like day-night difference. So that tells the amount of the data we need in the Cryo-EM. So higher the data or higher the symmetry will always help to boost the resolution or improve the resolution map. So most of the that's the reason like the membrane proteins they need a lot of more data as compared to the soluble protein. And also for the small protein, you need to increase the signal to noise ratio. You need a lot more data as compared to the large protein. And the same thing is if you have higher symmetry, you need less data. If you have lower symmetry, sequence symmetry, you always need higher, more and more data. So you can see here already we reached to the 2.6 angstrom. And what is the next step is because here we when we extract the particle, we bin them. So what we do it once we sorted out all the particles and we have good set of particles, we can go back. We can do it, we re-extract the particle. So to re-extract the particles, you can do this. Go here, and you can do the clone the job. You don't have to do everything from scratch. So you clone the job. All the input will be here. The micrograph input will be here. Only thing you need to change it. You need to remove these particles, and you need to use extract the particle that's already defined. So we put in them here. We have GPU. We remove this value. We still need to put the extraction in the box, but we don't want to do the cropping. So the pixel size will be 0.6, around 0.6. And re-extract this. So you can see here, if you look pay attention to the FSC curve. So FSC curve, we have a pixel size limit is 1.3. So that you can see that it's cutting the limit because when we plot the FSC curve, then we assume that Nyquist limit is 1.2 times of the pixel size. So that's why the cutoff is 2 times of the pixel size. So the FSC curve is cutting somewhere in the middle. So it's not reaching to the 0.14, but it looks if you extrapolate to the down 0.143, you can see whatever the resolution you will get. That's what the is showing here. So to make the FSC curve better, you need to re-extract the particles and then do the non-uniform refinement again. You can do okay. So what do we do? It just clone the job, but we can remove the inputs, or you can start go here builder and say okay, non-uniform refinement, and then get the particles from here. And then still you can use the model map from the non-uniform refinement initial reference, and then you will see all the plots will be way more better as compared to this one on the physical. Even though map looks good, there's no issue with the map, but our curve, the FSC curve does not look very good. So we go to the lower resolution, lower pixel size, and then we reprocess. Even at this resolution, if you pay attention properly, you can see the heavy side chains, or you can say aromatic side chain. They're already taking the shape. You can see them here. So since now the pixel the box size is larger, we're supposed to take longer than the previous job, but it still should not be. It should not take too long. Should be able to finish within the time limit. In meantime, let me open the Chimera. The module. Yeah, you can. There is a Camera X installed on this. You can load the module. You load the module for Camera X, and then you can open the map. So you can see here. Today, this one. And 20, job number 20. Not 20, but 19. So you can see here have the different maps. Okay, that runs for 4 iterations. You need to look on the sharpened map. Here you can see it better than the CryoSPARC. You see that one of the phenylalanine. If you use these are 25 images. If you use 1,000 something images, you'll be able to see the holes at the center of these things. Okay, so because of the size of the box, it's taking longer than so we might have to wait some time to see something here. It's already started the iteration 0, but obviously longer because of the box size. And then you can use this map to you can use any and download any epochate in PDB from the PDB PSP, and then roughly split in Camera X, and then you can use the Phoenix or Code Phoenix for the real space refinement, and then it should be ready to go. You might have to do some minimization, such as the ISOD. It also can be used in the Camera X that can do the real-time minimization, and you can manually, if something does not make sense to you, you can manually change it, the model, and then it will be the ISOD and make the model best fit in the map, and also the all the geometries for the PD will be corrected because it's doing minimization based on that geometries. Let's see. Yeah, so roughly I already gone through whole procedure from importing movie to this motion correction, CTF how do you prepare the images, then how you pick the initial block picking, and then you get the templates, and then do the 2D classification to get the better templates, and then do the template picking, and then again extract and then 2D classification. And after 2D classification, you do the ab initio. If you have ab initio model already from somewhere, either negative staining, PDB, or alpha model, you can use that. If you get the PDB from PDB, you can generate the ab initio, not ab initio, the map from that PDB using the Chimera. So the command is called the. You can use the command walk to get them to convert the PDB to prepare the map from the PDB and use that map to create to generate you can generate the template called the template create the template. So you can, if you have a PDB, you can generate the map from that in the Chimera, and then import that map into the CryoSPARC and create the template and use that map, and then use this create template job, and you can ask, okay, how many templates you want. It will create you the 2D class averages from that 3D model, and then you can use that template for the particle picking. So you can avoid the first step of a block picking and 2D classification, and then you do the template. That's one other way of generating the template. Another way is if you have tested and did some negative staining to screen your sample, you can use that negative stain data to generate the 3D model and use that as an initial, use that initial reference for the 3D classification or the refinement. So that will also work. Or if you have alpha, which dates you almost every protein, you will get some kind of prediction from the alpha fold. So you can use that as well and filter it the map to the 20 angstrom, 20, 30 angstrom to avoid the biasing, and then you can use that one as an initial reference or generate template for the template picking. All those will work. Or you can another option is called the topaz. So you can, this is topaz. It's kind of AI based. You train the software for the particle picking using the template, and then this also helps to improve the particle picking and also the number of particle picked. We know we already tested for this for the small protein, and using this topaz train and then this option, we can improve the resolution, not a lot, but like 0.1, 0.2, 150 bits when you got regular template picking. And also it's improved the number of final particles, 15 to 20% more as compared to regular. So that's also can be used for the improving the number of particles and also and so this might not finish. We already passed the 4 o'clock, so I don't know whether you guys want to wait, or it's not going to do anything different. It just improve what it's going to do. It's going to improve this map. Map will still be roughly the same. It might improve 2.5, 2.68, right? You might see the resolution improve 2.5 angstrom or 2.4 angstrom, but largely is going to improve the look for these FSC curve, because now at lower pixel size, the cutoff will be somewhere around 0.6. So the 0.6 means this plot can be extended better and then have the noise level somewhere here. So that's only thing going to change. Other than that, not going to change much. So if you want, you can end up the tutorial, or if you want to wait.
If anyone has any questions, you can ask now, or we'll hang around for a few minutes. And then we'll end the course. We'll have this recorded. We do have a previous session that we did on ACES, using CryoSPARC on ACES. It's on our YouTube channel. You can go to our main webpage, aceprc.tamu.edu, and in the top right corner, there's a YouTube icon. You can click that and search our videos for the CryoSPARC course. Gaya, do you know if there's a way to export like a history of your project? So if someone wanted to repeat the same steps.
So all the projects have the hierarchy here. See that?
Yeah.
It's a workflow.
Is there something with like details on parameters that were selected, the values that were selected? Or that's just yourself? Like if you wanted to share it? Oh, okay. Could you like export this?
It will export, but it will not export like when you hover your mouse over the dot, it will show the parameters. But when you export, it export as the PDF, not the so,
Okay, yeah, that's something we might can add to the short course page.
okay.
So someone can follow along and see the steps, because there's a lot of steps in here, and it would help if they had like a list flow chart.
Yeah, you see that? You can download it.
Yeah.
So, or
Okay, one question. How do we decide the number of images while selecting for patch motion? It says patch motion correction.
so the patch motion, there is a, you can do the same thing what I did with the after CTF. You see that have a the exposure curation. You can do here. You can go here and do the manually curate the exposures. Let's do that. And then see that it's doing the same thing, and it open up similar kind of thing, except it's just a motion correction. So it will have X and Y, the drift. So you can cut off and select the value you want to cut off. Let's say something is drifting hundreds of angstrom. You don't want to include that images. So if you see that that's the number of average intensity, that's fine. So total full frame motion distance. So if you remember after the CTF correction, we did this, and that's also show up this function here, and this total frame motion. So you can select set up this value. Okay, I only want the images that have the drift only 20 angstrom for full frame. And that's how you can discard all the other images that have a more than 20 angstrom drift between from first to last frame. That's the one way that's the way after motion correction. But if you don't want to you want to do it everything at one, you can do it at the CTF correction, after the CTF correction. So this is but that's obviously If you do it at this step, you can discard some of the images, then you don't have to do the CTF for the discarded one. So you can just discard either at the motion correction, after the motion correction, or after the CTF correction. So yeah, both at the both step it can be done without any problem. So now you can see, even though it's not the finish here, but the FSC curve looks way better. This will be improved later on, and now it's like a little noisy, but it will be improved later on. But you can see it's extending to the 1.3 angstrom. So you have a full range of cutoff. Previously, cutting off the cutoff is around 1.3. So the FSC curve is not even touching the line at 1.143 angstrom. Now it looks way better than 3, but it is going to improve with when it's finished at the later step. Only this is only the second iteration. It will run a couple of more 2 to 3 more iterations to improve it. And another thing for the space management, you can also, while your job is finished, you can go here and say, okay, clear all the intermediate results. It will only keep the end results that's useful for the next job, but it will remove all the intermediate files. So like the HPRC have this like limit of the files, not just a space, it also have limit for files. You can also clear the intermediate files to save the to save the limit for the number of files. Usually there's some mostly the refinements have a lot of iteration. So then let's have many intermediate files. That's useful, but for the regular like curation, these jobs don't have a lot of intermediate files, so not really useful. But for the refinement, 3D classifications, cleaning the intermediate results is always useful.
Okay, I guess we'll go ahead and end the session for today. Again, we'll have this recorded and we'll try to get that workflow PDF on the webpage.
Okay.
Thanks everyone for attending.